This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. So we started about transistor biasing. We already know that we need to bias the transistor. So having spoken with some of you after my lecture, I understand I think some concepts are still missing. So I will go through it again because there were some questions which made me to think that some of the concepts I explained was not clear, or so maybe I'll go through it today. Again, I want to make sure that you understand the concept because I'm scared of my life. You will be designing some, medical devices or aircraft electronics. So we need transistor biasing. Without biasing, we can't use the transistor for any real application. So when you bias the transistor, in order to operate a transistor as an amplifier, mostly we use the transistor for amplifying signals. We make so many voltage amplifiers using transistors. So when we make a voltage amplifier, we have to make sure that a transistor is operating in the active region. For that, you have to make sure that your base and emitter is forward biased, then base and collector is reverse biased. So that is a basic requirement. But when we do the basic requirement, we will come to know many issues, whether our biasing is a robust biasing or not. Because biasing, we can make many biasing schemes, but then the question is whether that is a robust biasing scheme, whether it is a very good one, like whether it is affecting any parameters, like is it sensitive to temperature. Your biasing means you vary one resistor, whether your bias points changes. So these are the concerns. So then people came up with so many biasing schemes, and then that's what we are discussing. And or how the biasing evolved. We are studying different types of biasing. Like I give you a transistor, and each one of you I give you a transistor, and then I can say, okay, our requirement is base emitter should be forward biased, base collector should be reverse biased. Each one of you may come up with different types of biasing. But then the question is then which one is good? How we can find out which biasing is good? That's what we are going to do. Obviously, this biasing here we don't have any biasing actually. The forward biasing is absent here, so that you don't get any amplification, which we already did. So we need to make sure that we need proper biasing here between base and the emitter. So we can't connect a microphone here. Then we need some voltage here, VB. That voltage is VB, the voltage between base and the emitter. Then in order to give a voltage, we can't connect a battery because that is not practical. Then what we do is we already got a power supply. Then we will be connecting a resistor. So that is called a biasing with the base resistor. And then this has been proposed. Okay, it's a good biasing because you are connecting VCC here, then you can connect an RB here. So your VCC equal to IBRB plus VB. Then in the transistor, then we have to make sure that we choose this RC and RB properly so that you get a reverse bias between base and collector, forward bias between base and the emitter. In order to do that one, we have to write down the equation, and then only we can correctly bias it, because we are connecting these resistors. Without writing down the equation, how can you tune it? That's the reason we are going to write down the equation. Then also we want to find out whether this bias is a good one, whether it is depending upon beta, temperature, resistor variation. We want to check it. So that is the reason we are writing down the equation. Otherwise, we don't need to write down the equation. IBRB plus VB equal to VCC, which I already discussed. From that, you can get IB. And then IC equal to beta times IB, then VCE, we can find out VCC minus ICRC, which is equal to VCC minus RC is here, IC is this value, substitute here. But then in order to make sure that your transistor is in the forward bias region, you already got this RB here. In order to make sure that your transistor is in the reverse bias region, what you have to do is your VCE, this voltage should be more than the base. Then only this will be reverse biased. So then we make a condition. So this VC should be always greater than VB. So that is a condition. So if you meet this condition by tuning these values, because RC is a constant, RB is a constant, VCC is a constant, beta again is a temperature dependent, VCC is a constant. So if you can satisfy this equation, your transistor is operating in the active region. So this is a biasing, is a good biasing. We can say, okay, at least your transistor is in the active region. You can use for some amplification. You can connect a signal here with a capacitor here, and then you connect a signal, you get amplified signal here. But then the question is this biasing a good biasing? This biasing is not a good biasing. Why? Because you are going to design this circuit. So when you design this circuit, maybe I should draw it. So when you have this circuit, so this is your VCC, this is your RC, and then this is your RB, and then this is a IB, and then this one anyway is grounded, so this current is IB. So this is a biasing, so this is a VCE. But then the equation we have got is VCC minus beta times VCC minus VB by RB, okay, it's clear, into RC, which is greater than VB. So when you get this equation, then I am going to ask you, okay, we got this equation, can you please bias it? But then when you say that, okay, I can bias it, but then when you try to do it, you will find some problems. The first problem arises is, in order to fulfill this condition, your VCC is known. It is already given 5 volt. Beta, for a given temperature, I am going to ask you to do in the room temperature. So you can get beta almost from the transistor, you can get it. You can trust that value, maybe 100, because in the room temperature, it is not going to fluctuate much from the value that is given in the data sheet. Again, this VCC constant, RB, you can put in an RB. But then you've got RC, again that is a constant. But then you have VB. So what will happen is, like you will choose VB equal to 0.7. Maybe somebody else will choose maybe VB equal to 0.75. So which one is correct? So there is a problem. So VB is around 0.7 because this is here you have got a diode here. That's the reason we say that it's a forward bias around 0.7, but we don't know what is the actual value. It could be 0.69, 0.68, 0.71, 0.72. So we don't know. So there is an uncertainty. So we don't know the VB. And then if you assume the VB, suppose I assume the VB, that is equal to 0.7, then how can I make sure that this 0.7 is correct? Actually, the 0.7 is not correct. So this equation is not, this biasing is not good. We have to assume some VB, but then that VB not the actual VB you are assuming. Second one is, so that is a VB problem. So VB not know exactly. Second one, beta sensitive to temperature. So this beta, as I said, your circuit, the beta varies with respect to temperature because the electrons coming out of the emitter to the base and to the collector, these numbers vary with respect to the temperature when you heat up. So your performance, the biasing might be varying. The bias points might vary when you take it to Saudi Arabia or when you take it to Iceland because of the temperature difference. So this is not at all good. Then coming back to this VB issue. In the VB issue, then what I will do is, maybe I don't have any other option, I don't know any other biasing, then I will choose maybe VB equal to 0.7. Then somebody asks you, how can you prove that this is wrong? VB equal to 0.7, or somebody can ask you, how can you make sure that this is correct? Then what I can do is, I got VB equal to 0.7, and then using, I know that IB, what is the value of IB? Which is equal to VCC minus VB by RB. So what I will do is, I will put this value here, and then I will get IB. Then I will find out IC, which is equal to beta times IB. Then what I will do is, I can find out, that IC equal to IS exponential VB by VT. So I can write VB. So what is the value of VB? IC by, what is the value of VB here? Yep. So VT. So this is the equation for VB. Then what I will do is, I will substitute this IC here, and then I will check whether I am getting this 0.7. If that is the case, it is correct. But most of the time what will happen is, when you do it, you assume 0.7, when you calculate you may get 0.68. Means this assumption is not correct. Then what will you do? You will come back and vary this one. Then you will check it whether assumed value you are getting here in the back calculation. So when you do so many times iteration, maybe you can find out which one is matching. Then here your assumption is 0.69, and here also when you calculate you are getting 0.695, maybe the third digit only variation, then your assumption is correct. You know what I meant? So then you have to do the iteration. So we will do a problem later. So that's how we prove that our assumed value is correct or not. We can prove it, whether your assumed value is correct. or if it is not correct, how to make it correct. So that's what we do. So then this one, then we have to do the iteration and then we have to find out. So it is not a good biasing. So then we went to the next biasing. So the next biasing is we connected two resistances. So again here, you got some questions. So when you have two resistances, what we are doing is we are making sure that this voltage, so this is your VB. So now we think that we got control over VB, because now we can make sure that this VB, this voltage, we can set it using R1 and R2. But then here also there is an issue. When you have this type configuration, so a basic question. So you got two resistances, R1, R2, and then this point is maybe Vx, and then you got VCC. So what is the value of Vx? That is equal to R2 by R1 plus R2 into VCC. So that is correct. There is no confusion. But, oh sorry, yeah. So then this equation you can see R1 plus R2 and then Vx equal to R2 into VCC by R1 plus R2. This equation is definitely correct. But then the problem is soon after, then the current is coming, maybe IC current is coming, that is going through the resistor, that is going to the ground. But soon after this current is branching here. See, in this configuration, if I connect to maybe a transistor, or you are tapping some current from this part, VCC, then your Vx, I can only write approximately R2 by R1 plus R2 into VCC. So this may not be very accurate, because some current is flowing this way. So if no current is flowing, only we can write this equation. Or we have to assume that this current is very, very small, negligible. In that case, we can write Vx equal to this X. So Vx equal to R2 by R1 plus R2 into VCC. Otherwise, what we will do? Then if this is the situation, what will happen? If you are taking some current from here, we will be doing Thevenins. That's the reason we will find a Thevenin equivalent circuit. Thevenin voltage. That's how you might have studied Thevenin's theorem and Norton's theorem in the undergraduate degree. So then we will find out Thevenin's resistance, Thevenin's voltage. I will discuss. So then here in the resistive biasing here, our first assumption, what I am going to do is the current going to the base is very, very small, which is true. The base current is very, very small compared to the large current that is coming from here. So if we can make this current is very, very small, then I can use the equation Vx equal to R2 by R1 plus R2 into VCC. Then if the current we are bit more, bigger value, then we have to use the Thevenin and not Thevenin's voltage, Thevenin's resistance, and then put in the values. I will show you. So in this here, first our assumption is a simple assumption. Your base current is kind of, very, very small, can be neglected. In that case, I can write, this one is when the base current is a little bit, higher. I will discuss this one later. Then Vx. So this situation is different. We are not taking into account the Thevenins or Nortons. Our assumption is that this current is very, very small, neglected. Vx equal to R2 by R1 plus R2 into VCC. IC, we already know, Is into exponential VB by VT. And then here VB, we already got it. That is equal to Vx. So here when you think, see, IC equal to Is into exponential R2 by R1 plus R2 into VCC by VT. So when you look at this equation, that is your equation for collector current. From that you can find even VC. But here it is relatively better. Why? Because now in the exponential term you got R2 by R1 plus R2, only a ratio. So if you can choose same type resistances with respect to temperature, resistances changes uniformly because you got same type of material, so that it will cancel out. VCC is a constant. For a given temperature, again you got a little bit nasty term, that is VT. So VT is again temperature dependent. So definitely there will be an effect on the temperature. Then Is also will a little bit affect on the temperature. But then this one is not, at least not depending upon the beta. It is not sensitive to beta. There will be some variation in the circuit, but not like beta, because beta variation is more prominent, because beta is the current gain. So that if that is varying from 100 to 120, then there is a big variation. So this one is relatively better, though there is some temperature dependence. It is better because it's not depending upon the beta. Then another thing is a little bit dependence on the temperature. Another thing is even it's not affecting much on the resistor. The temperature dependence of resistance is not affecting here because of the ratio. So this is relatively better. And then IC is relatively independent of beta if base current is small. I said base current is small. Why? Because when I go back to this circuit, so here what happens is you got the VCC. Even this circuit, there is another issue which maybe I should discuss first. So here what will happen is when you increase the temperature, then your VCC also can vary a little bit to the power supply. If you don't have a band gap reference circuit, in the mobile phone, in your laptop, they have got band gap reference circuit. Band gap reference means you got your battery, then the battery is connecting to your band gap reference, and then it is powering all the electronics. So when you have band gap reference means that produces a golden current. We call it as a golden current. You will study later in the constant current source, the current, when we study current mirror. So the band gap reference will generate a golden current that will be constant irrespective of the temperature. So even though you put in a battery, because you got this band gap reference circuit, your mobile phone, the performance is not affected when you take it to different countries having different temperatures. But then most of the time you don't have band gap reference readily available, means we integrate in the chip the band gap reference. If you don't have band gap reference, when you increase the temperature, this VCC will increase. Here, when the VCC is increasing, what will happen? This current will increase. Say VCC fluctuated 10 times. So VCC fluctuated 10 times means you got here some current, and then your base current fluctuated 10 times. Then your collector current, how much it will fluctuate? Beta times that much fluctuation. So this is a big fluctuation. So this is also not good. But then here, there is one advantage. When you increase the temperature, so this is relatively independent of beta. Even when you increase the temperature here, there is another advantage. Why? Because when this VCC is increasing, this current will increase, maybe 10% fluctuation, increment in 10%. So here it will be 10%. But then because it is coming only a small current here, the fluctuation here is much less. It will not be 10%. So that the IC will not vary much. For that we will put in some values. So that is the reason I put in some values, 17K, 8K. Somebody asked whether I had to put in big values here. Yeah, you don't need to put in very big values, but relatively bigger value will be good so that you can avoid the power dissipation. You don't want to pump more current to the ground. So you can put in maybe kilo values might be good. Not a good idea to put 1 ohm here, 3 ohms here, 5 ohms here. That is not a good design. Or even 100 ohms. So 17K, 8K and 5K, 2.5. So when I calculate, then IS I got from the data sheet, beta I got from the data sheet 100, and then Vx equal to this value. Our assumption is this current is very, very small, and then that is equal to 800 millivolt. I find out IC, which is equal to 231 microamps, so that I can find out IB, see 2.31 microamps. So I can find out VCC by R1 plus R2, so that is this current. So that is equal to around 100 microamps. So the 100 microamps is flowing here, and then only 2.31 microamps is flowing here. So this equation is okay. It's not, not wrong. So we can assume this is approximately equal to R2 by R1 plus R2 into VCC, because this current is only 2.31 microamps, but 100 microamps is flowing here. But then now you can check your 100 microamps. So your IB equal to 2.31 microamps. That is equal to 43 times more than this current. Then now I can come back to the fluctuation. So if your VCC is fluctuating 10 times, then this current, VCC by R1 plus R2, this 100 microamps, that also will fluctuate 10 times. But then your VB, this IB, that current is only 43 times smaller than this one. So that your fluctuation will be 10 times divided by 43 times. The fluctuation is very, very small. Because this current is big, 10% fluctuation in this big current, but then from that you are taking only a small portion, and then because it's only 2.31, so this will be fluctuating only very, very small. So the IC also fluctuating very, very small. So that this is relatively better compared to the previous circuit. So VC, we can find out VCC minus ICRC, which is equal to 1.354 volt. And then the only problem here is because you have got exponential IC, got an exponential dependent on VB, which is equal to R2 by R1 plus R2 into VCC. And then if you replace one resistor, like you are working, this circuit is working properly, or you have designed this circuit for 1.345 volt, maybe in a chip. And then what happens is, but when you fabricate this resistor, maybe slight, something happened in the fabrication, there is a kind of a tolerance, it became 8.1 kilo ohm, very small. Then what will happen is, your VC will become 1 volt. See, you don't get the performance. So that is the only issue. That is because of this exponential dependence this circuit is having. Then if you assume that this current is relatively bigger, then we have to go for the Thevenin circuit. So Thevenin's means then what we will do is we will find out the Thevenin's equivalent circuit. So Thevenin's, that is the reason I have shown here. So then what will happen is, so Thevenin's, so R Thevenin's from this circuit we already got it. See, we got, so when you have these resistances R1, then you got R2, so VCC, and then we can find out RTH, R Thevenin, which is equal to R1 parallel R2. Then we can also find out VTH, Thevenin's voltage, that is equal to VCC into R2 by R1 plus R2. So that is a V Thevenin. Then we can represent this as C. So I got a V Thevenin, and then you got a R Thevenin, and then it is going to your transistor, and then this is your VB. So now you can write down the, so what is the base current now? Then this current is IB. So now I can write VTH, that is which is equal to IB into RTH plus VB. So then VB, which is equal to VTH minus IB into RTH. So then when we write IC, which is equal to IS exponential VB, which is equal to VTH minus IB into RTH divided by VT. So if the base current is the kind of, if in this here, in this in the slide, if the base current, if you are not neglecting the base current, then your IC equal to IS into exponential VTH minus IB RTH by VT. And then if you not neglecting base current, so if you neglect the base current, so VTH equal to Vx, so which is equal to R2 into VCC by R1 plus R2. So this one is only VTH equal to Vx only when your base current is neglected. So otherwise you have to get the Thevenin. So in the problems I would recommend you to get Thevenin, equivalent to Thevenin voltage and Thevenin resistance, and then do the calculation, which is easy. Thevenin's theorem is much easier. Maybe Norton is a bit more difficult, but Thevenin is easy. Yeah, then we'll come to, yeah, so we said this is improved, but then still it got some issues because this is sensitive to the resistor variation. So that is a problem when you fabricate the device or when you replace one resistor value. Then people came up with the idea, then we can make degeneration, emitter degeneration biasing. Means there, here we are connecting a resistance here after this diode. Means the diode part means forward bias. Here you got a forward bias. After that they are going to connect a resistance here. So this is called a degeneration. So the degeneration, sometimes people get confused. Maybe an analogy will help you to understand the degeneration. So what is this degeneration? So what it will do to the circuit? Maybe this is an analogy. I wouldn't say that exactly because this is a transistor, so I can't use a diode to explain, but this will help you to understand. So I got a, maybe I got here 0.7 volt, and then I got a diode, and the forward bias is around 0.7 volt. So I will connect a diode here 0.7 volt, and then this is ground. So maybe I will draw it in another way so that then you will be able to answer quickly. So 0.7 volt. So this is kind of the input part of the transistor. So this is just for an explanation because this is a transistor. So maybe this is X and then maybe this is Y. Okay. So this is just for an understanding, analogy. I told you it's an analogy because I can't use a diode for explaining the transistor. But then this definitely will help you to understand the concept, why we need a degeneration. So if I put 0.7 volt, what is the voltage here? So the forward bias of this diode is around 0.7. So if you got 0.7, how much you get here? Yeah, 0.7. How about if I put exaggerated value? I am going to put here maybe 0.8 volt. How much you will get it? How many of you think 0.8? If diode drop is 0.7, how can you get 0.8? Okay, again maybe exaggerated, 1 volt. How much you will get here? You won't get 1 volt because you got a diode that will make sure that that is a drop is only forward by 0.7 volt. Then what will happen to the remaining voltage? So when you increase the voltage, this is a diode, that's the reason the current will increase and burn this diode. The remaining voltage, it will be 0.7, but then remaining voltage, it will increase the current and then it will burn the diode. That is the reason when you increase the voltage, diode will burn it. So then how can you avoid this one? So nobody will connect it like this. When you have a diode, nobody will make such a connection. So if you are designing the circuit, then what you will be putting, something will be putting. Yeah, so most of the time what we'll do is we'll put a resistance here. So 0.7, so maybe it's 0.8, 0.7 will be here, 0.1 volt will be here. So when you increase, somebody increased 1 volt, still it will be 0.7, then 0.3 will drop across this R. So it is kind of absorbing, the variation. So same type of principle we are applying to transistor. Such a reason this emitter degeneration, that's what we are doing. So even though here you got some fluctuation, then the VB is not affected much. That will appear across this RE. So that's what we do here. And so this one is good. And then here we can say that again Vx, which is equal to R2 by R1 plus R2 into VCC. My assumption is this current is very, very small. VP. So now we got a VP. So what is VP? So Vx equal to VB plus VRE. VRE is the voltage across RE. So I can write VP equal to Vx minus VB. So Vx minus VB is the voltage across this resistance. So IE, what is the value of IE? That is equal to VP divided by RE. What is the emitter current? Because this, if you know this voltage drop, you can write VP divided by RE. Yeah, so we got the value of Vx, R2 by R1 plus R2 into VCC, Vp equal to Vx minus Vb, because Vx equal to Vb plus IE into Re, that is VRE. And IE equal to current through this resistor, that is equal to Vp. What is the voltage here between this point and ground divided by Re. Then I can write this equal to 1 by Re. So what is the value of Vp? Vp equal to Vx minus Vb, Vx equal to R2 by R1 plus R2 into VCC, substitute here, and then IE. And then this emitter current, most of the time it is approximately equal to collector current. We can say that this is a collector current. Means your emitter current equal to base current plus collector current. But base current is very, very small. Here I already said it's a very, very small. That's the reason I have written this. I haven't used Norton's voltage and Thevenin's voltage and Thevenin's resistance. So this base current is very, very small. That's the reason we neglected this one. So I can write IE equal to approximately equal to IC. So this is the expression for the collector current. And then if you are not neglecting the base current, you have to write down R Thevenin and V Thevenin. The presence of Re. So this presence of Re helps to absorb the error in Vx. So Vb stays relatively constant. That's the reason I have shown you using the diode. If there is a little bit fluctuation, that is not going to affect your VB. Means even some voltage is fluctuating because of some reason, this point, and then what happens is it will be dropping across this one, because we are providing this resistance so that it can dump that variation to this resistance. This bias technique is less sensitive to beta and VB variations, because VB is the base voltage variations. If you make I1 greater than IB, the same what I said before, this current we make it bigger, that is flowing through R1 and R2. This current is bigger and this current is very, very small. Then we can make this kind of less sensitive to beta, because 10% fluctuation, here it will vary 10%, but then here it will not vary 10%, it will vary much less than 10% depending upon what is the current you are getting here. If this current is 100, if this current is 1, then if here it is 10% fluctuation, then here it will be 10% divided by 100, that is the fluctuation here. It is very, very small. Then we are going to put in some values, because without putting in the values, we don't make any sense. So I'm going to put 16K here, 9K here, 100 ohm, that is Re, then VCC equal to 2.5 volt, and 1 kilo ohm, then beta equal to 100. Beta, then IS I got from the data sheet, that is approximately equal to 5 into 10 to the power of minus 17 amps for this transistor. I will find out Vx 900 millivolt, Vp, Vx minus Vb, which is equal to 100 millivolt, IE, emitter current, Vp by Re, so which already got it, which is equal to 1 milliamps. Vb, so I am going to find out Vb, which is equal to Vt ln Ic by Is, which is equal to 796 millivolt. Vy, so the voltage at here, which is equal to Vcc minus IcRc, which is equal to 1.5 volt, because we already got Ic, we already know Rc, we know Vcc. And then minimum Vy allowed. So what is the minimum Vy allowed? Why I said this one? So this is 1.5 volt, but then I have written also minimum Vy allowed. Why this is the case? Yeah, because we have to make sure that the minimum, this 1.5 volt is here, but then somebody will ask what is the minimum voltage at collector, that is Vy, to make sure that a transistor is in the reverse bias between base and the collector, in order to make sure that it is in the active region. So minimum Vy allowed is Vb minus 400 millivolt. Because if you put Vy much below this value, what will happen is your transistor is in the saturation region, deep saturation. So Ib equal to 10 microamps is less compared to current flowing through R1 and R2. So you can find out Ib. So this Ib, because you got Ic equal to 1 milliamps. So if you divide it by beta 100, so 1 milliamps divided by 100, so Ib. So that is equal to 10 microamps. So this is 10 microamps. So that is the reason I said it's very, very small. And then current flowing through R1 and R2 is, you can find out Vcc divided by 16K plus 9 kilo ohm, then you will get 100 microamps. So your Ib is much, much less than R1 plus R2, means the current flowing through R1 and R2. So that's the reason I can use this equation. And then that's the reason when you have 10% fluctuation here, then your collector current, your current through this R1 and R2, that is 10 microamps, might increase to 10% increment. How much is the 10% increment? Yeah, maybe 110. No, so 100 microamps is flowing, so you got 10% increment. Yeah, 110. But then how much this base current will increase? Yeah, 1 micron. So it's very, very, very small. See, only here 1 micron vary, when here 10% is varying. So 1 is how much of 1? So when 10% fluctuation is here only 1% fluctuation. Because depending upon what is the ratio here. So that is the reason this is good. Then if R2 increased to 9.1K, so that's what we want to check. So now we are going to increase 9.1. So R2 increased to 9.1K, then your Vx will become 9.6 millivolt, 906 millivolt Vx instead of 900 millivolt. Emitter current, which is equal to 1.06 milliamps. See here, instead of 1 milliamps. And this will cause only 9.4% variation in IC. And then Vy, your Vy will become only 1.44 volt. Now your Vy equal to 1.5 volt. See, now even though you increase only 0.1, it did not affect much. But in a few cases here, how much it varied? 1.5, 1.44, only 0.6, 0.66. But then if you go back here, in the previous case, this one also is less sensitive to beta. Because of this, we are taking only a small current here. But then here, this circuit, the main problem, not this circuit. So in the previous one, here the main problem with the circuit is here also, if you choose IB much less than Vcc by R1 plus R2, then it is less sensitive to voltage fluctuations. And this is already insensitive to, almost insensitive to beta, because you don't have any beta time here. But the only problem with this biasing is, if there is a fluctuation in the Vx, your Vb will change. And also, if your R2 is varying a little bit, then your Vc changed by this much voltage, 0.345 volt. That is a big variation when there is only a small variation in the resistance. But when you put this biasing, the advantage is even though Vx is changing, you don't have much problem, because that will appear across this Re. Then with respect to resistance variation, we have found only a very small variation. See, your Vy, that is equal to 1.5 volt, and then that is only varied to 1.44 volt. The fluctuation is very, very small. You know what I meant? So that is the reason this biasing is, I wouldn't say that the best biasing, but this biasing is largely used in the transistor amplifier circuits because of these reasons. So this circuit has the following advantages. This circuit is the biasing is a kind of insensitive to beta variations, to some extent insensitive to the temperature fluctuations for the power supply, insensitive to this voltage Vx, this bias voltage fluctuations, and then this also kind of insensitive means within the acceptable level. If you vary the resistances, means 9.5% variation is acceptable. Below 10% is kind of considered acceptable. So this biasing is much better than the previous biasing schemes. Then I think I will continue. Just. So there is one more biasing people use, that is called self-biasing technique. So this is another biasing that is called self-biasing. So here what people do is, so they got RB, but they are not connecting to the VCC, but rather they connect to this Y point here. So when you connect to this one, so what is the advantage? So what is the value of Vy and Vx? So RB is, maybe I'll say RB equal to 0. Then what is the Vy and Vx? So the transistor will be in the edge of saturation. But then can this configuration saturate? Can this biasing can saturate? Yeah, this configuration, the advantage is if you put RB equal to 0, you can see a good picture. Your Vy equal to Vx. Means voltage at the collector equal to voltage at the base. So that is means this transistor will come and stuck in the edge of saturation. It can't saturate. So this is called self-biasing. In the self-biasing, IC, which is equal to VCC minus VB by RC plus RB by beta. So how can I get this equation? So you can you apply the Kirchhoff's law, and then you can easily write down. Maybe I'll start from here. So Vy, what is the value of Vy? VCC, so we are because this circuit have two branches. So one branch is here coming to the collector, going through the transistor, coming to the emitter. Another branch is coming here and then going to the RB and then coming through the VB and coming to the ground. So if I apply Kirchhoff's law to this branch, that is a vertical, this branch, collector, emitter, your Vy equal to, so VCC equal to Vy plus IC into RC. That's the reason Vy equal to VCC minus IC into RC. So Vy, which is equal to, you can also write Vy because Vy got two equations, VCC minus IC into RC, and also we can write C using this branch, Vy equal to IB, RB plus VB. And then you can write which is equal to RB into IC by beta because IB equal to IC by beta plus VB. That's the reason we got IC equal to, from this equation, VCC minus VB by RC plus RB by beta. It's a simple substitution. So this circuit is used in optical communications because this configuration can operate at a very high frequency circuit. They use it like 40 GB per second, gigabit per second, that type of data rate. People use this type transistor biasing, that is self-biasing. So the design guidelines, so you have to make sure that your RC is greater than RB by beta. So why? If you don't follow this rule, what will happen? Look at this equation. Yeah, but then what is the advantage? So this biasing, if you look at this equation, you have to think carefully. It's got a beta dependence. You know what I meant? See, your IC, you got beta here. But then we can get rid of this beta fluctuation. If you put RC much greater than RB by beta, then this term will go. Then your IC equal to VCC minus VB by RC. Then Also, we have to make sure that delta VB much less than VCC minus VB, so that why we need that one? Yep. So this bias technique utilizes the collector voltage to provide the necessary Vx and Ib. One important characteristic of this technique is that collector has a higher potential than the base, thus guaranteeing active operation of the transistor. But still, even if you check it here, then still you got that VB issue. You know what I meant? The VB we don't know exactly. So this one is another disadvantage. But then this one is a kind of widely used because of this advantage. It will be always in the active region. Provide insensitivity to beta, provided if you put RC much greater than RB by beta. Otherwise, there is a beta sensitivity to IC. So provides insensitivity to variation in VB and high speed of operation. So this can provide high speed and then insensitivity to variation in VB. So design procedure. So how to design? Choose an IC to provide the necessary small signal parameters like GM, RPi, because IC is depending upon GM and RPi. Considering the variation of R1, R2 and VB, choose a value for VRE. I am talking about biasing with emitter degeneration. When VRE is chosen, VB is calculated, Vx can be determined. Select R1 and R2 to provide Vx. So this one, when you read now, maybe you will think, will not make much sense. When we do some problems, you will make, sense of it. So I will keep this slide, and then later when you do some problems, you can come back and read. That is a design rule we will be following. So summary of biasing techniques. Input and output impedances. For an ideal voltage amplifier, the input impedance is infinite and output impedance equal to 0. 3 different transistor biasing schemes discussed. Not actually 3, maybe I can say 4. Because these one are kind of in the same category. So first one, sensitive to beta, sensitive to resistor error. This one, this is insensitive to beta, almost insensitive to beta. But then we came up with these two designs, always in active mode, and then here it is insensitive to resistor variations, insensitive to these fluctuations, and insensitive, almost insensitive to beta, and then this one also is good. And then this one is, if you put RC much bigger than RB by beta, then we can say that it is insensitive to beta, but then the advantage is this is always in the active region. Then another one is the transistor topologies. So these are, now we know the biasing techniques, we know that why we should be caring about different biasing. We also got some idea about beta dependence, fluctuations in the circuit. Now we will be discussing about transistor topologies. Transistor topologies means transistor is a 3-terminal devices. You got 3 terminals. Then people might ask, okay, you got base, emitter, collector. How many inputs? Can I connect my input to collector? Can I connect my input to emitter? Can I connect my input to base? Or output, can I get output from base? Or output from emitter, output from collector? Because we have to find out how many combinations we can use the transistor for making amplifier. So this is called transistor topologies. So these are the topology. Either I can connect a signal here, input topology. I can connect an input signal to the base, input signal to the emitter, or input signal to the collector. Output, I can take output from collector, I can take output from emitter, or I can take output from base. So how about the first one? Can we do this one? Definitely, we already discussed it. We can connect a signal to the base. Then how about the second one? Can I connect the input to the emitter? Yeah, emitter also it is possible. So you have to think about the semiconductor that representation. Then the emitter is fine. Then how about collector? Can I connect the signal to the collector? Will I get something? So collector base, if it is the active region, collector base is reverse bias. It will not work as a transistor. So you can't. Then how about this output? Can I take, so input you have only 2 combinations. You can't connect input to the collector. Then how about collector, output at the collector, which we already know. Then how about the emitter? It's simple. Emitter, is it possible or not? Possible. How many? Not possible. Why it is not possible then? So because if here when you are connecting, you are getting the collector current. Your emitter current is approximately equal to collector current. So same variation you will find in the emitter possible. Then how about taking output from the base? No, it is not possible. So then you got how many combinations? So you can use 4 ways. So there will be common emitter. So here it's a common emitter is common to collector and the base. Then common collector. So collector is common here. Then we got a common base. So we got 3 topologies here, may be common emitter, common collector, common base. So we will be studying these 3 topologies in the coming lectures in detail. So this is a common emitter which we already started discussing, because emitter is common. See, emitter is grounded. You apply voltage at the base with respect to the emitter. Collector you are measuring with respect to the emitter. So this is common emitter. So this is emitter here is common. So this is a common emitter or CE topology. So we will study CE topology, then we will study common collector topology, then we will study common base topology. While studying, we will find where are the applications, where these topologies are used. Maybe I'll continue in the next lecture.
I'm coming in and just say, they'll come out because maybe the other lecturer might want to come in. Yeah, please.